All right, good morning. First thing I should preface here is that I know a lot of you are struggling with these problems. They can be a little bit challenging. They're word problems. Nobody likes word problems. I'm going to post 3 videos today, going through the 3 problems I assigned you to do yesterday, and hopefully that'll. The only way that you're going to get through these is to continue practicing them. So let's take a look at this problem. First one I assigned for yesterday. A trough is 12 feet long, 3 feet across the top. The ends are isosceles triangles with altitudes of 3 feet. Water is being pumped into the trough at 2 cubic feet per minute. How fast is the water level rising when the depth H is 1 foot? I'm going to just go ahead and quick copy this question. Hope that copied. We'll see. Do that. There it is. Water is being pumped in the trough, and it didn't give us all the information we needed, so we'll delete that. Oh well. It actually put it up here as well, which I didn't want it to do. So, looking at this diagram, it's important for us to get some important information out of this. First of all, always look at the shape you're dealing with. Now, this is what we would call a triangular prism. And we say that because it has a cross section here that is an isosceles triangle, and it maintains that same shape as a constant throughout its length. We would call this a regular prism. Any regular prism has a cross section that remains constant throughout its third dimension. That's useful to know because anytime you have a 3-dimensional shape like this and you're unsure about what the volume of that shape is going to be, if you can find the area of a cross section that remains constant and multiply it by the length, you then would be able to write a volume equation for this. Some key things here. This 2 feet cubed per minute is very important to us. And the reason that's important to us is it's the first thing that tells us, the picture does as well, but feet cubed per minute, the fact that we're given a cubic unit, feet cubed, tells us we're going to have to deal with the volume of this shape. And that is important to us because we need to know what equation we're going to be writing. So I'm going to start here. And if you've ever used Google Docs for this before, I bumped up my font size to 24. And I'm going to go to Insert an Equation. And I'm going to go ahead and type in the volume of this figure is equal to, and it takes a little while to get used to how to type equations in here, but a triangle is 1/2 its base times its height. And because we're 3 dimensions now, we have a length of this triangle. We're also going to multiply it by length. And that's going to be our volume equation for this figure. Okay? So that's the first important thing we have to identify. So now we're going to start looking at some given information for us here. And the first thing we're going to look at here is this 12 feet. Length equals 12 feet. That is very important to us. And the reason that's very important to us, I'm going to do that as an equation, so that's in italics as well. The reason that's very important for us, length equals 12 feet, is that as we pour water into this shape, the water level is going to rise, so the height of the water is going to change. The width of the water is going to get wider as we go up, so the base of our triangle is going to change. However, no matter what, that 12 feet across there, that is not going to change. That is a constant. That's important for us because constants we can plug into our function immediately. constants don't change, so we don't have to worry about what happens when we take the derivative of a constant. All right, so we're going to go ahead and we're going to plug that in. We're going to say volume is now equal to 1/2 base times the height times 12, and that is equal to 6 times base times. We've simplified our equation drastically, going from 3 variables down to just 2 variables. The next thing, and this comes out of geometry, is they tell us this is an isosceles triangle. We're always using this angle here at the point. If you are to draw lines parallel to this base, which is 3 feet, anywhere along this triangle, you're going to get what we call similar triangles. That is, triangles with the same angles, but different side lengths. The key with similar triangles is similar triangles maintain a ratio between their dimensions. So we have this height of 3 feet, we have this base across the top of 3 feet. Our base and our height are in a 1-to-1 ratio. That will always be the same. When the height is 2.5 feet, the base will be 2.5 feet. When the height is 1 foot, the base will be 1 foot. That ratio of 1-to-1 will always be maintained. So our base will always be equal to our height. Now, the next important thing we have to identify here is what are they asking us to find? We'll go back to this question. We're going to have to pause there. Okay, welcome back. I hope we're recording again. So there was a fire alarm, as you all know. So where were we at here? We've got our volume equation. We know that our length is constant. We plugged in our constant length, simplified it. And we also know now that base and height are going to be equal. I'm going to space this out so it's a little further away. Base and height are both equal. Next important question, what are we being asked to find? It's important to identify what you're being asked to find and to give it a calculus rate notation. They're asking how fast is the water level rising when the depth is 1 foot. And they define depth as h, which we would expect. So how fast, as we're pouring water in here, obviously the water is going to be rising. It's going to be getting wider. So there are 2 changing dimensions that they could ask us about. One would be the base, the width of the water, and the other is the height, the depth of the water. They're asking us how fast is the water level rising? How fast is that height changing? So we want to make a note of that. What are they asking us to find? I'll put it in as an equation. Okay, since the height is defined as the h variable, dh, as time changes, is equal to question mark. They're asking us to find out how fast that water level is changing. And they're asking us to find it at a specific point. They're asking us to find it when height is equal to 1 foot. Okay. First thing we're going to have to do is we're going to have to take the derivative. Hold on. Something else we have to do first. We're looking for dH dt. Our equation right now, okay, is volume is equal to 6 times base times height. Base times height is 2 variables. They're multiplied together. That indicates a product rule. We don't want to do a product rule if we don't have to do a product rule. Since we have this equivalence, this known fact that the base and the height are always equal, we can replace B here with H, okay, because of that equivalence. So we're going to write a new equation here, and we're going to call it volume as a function of height is equal to, we don't really need that, we'll just say volume is equal to 6 times h, and h times h is h squared. We have a very simple volume equation here. Now, I want to point out, when we plugged this 12 in, this 12 was feet. So while we don't have it shown here in our equation, this 12 times the 1/2 became a 6. This is actually has a unit of feet with it. So this is actually 6 feet. So when we multiply by h and h, we get feet cubed, which is what we need here. Okay? Our next step, that we are going to need to find the derivative of this. Volume equal to 6h squared. We need to find the derivative of this equation, and we're taking a time derivative. Last week we talked about doing implicit derivatives of variables other than the independent variable in the problem. In this case, time is our controlling fact here. As time goes by, more water gets poured into this. So we're going to take a t derivative of this. Derivative of volume. New equation, fraction. Why did it get small on me? Enter new equation, fraction. We've got dv over dt equal to, now do a power rule, 2 times 6, it's going to give us 12, h, and because it's time derivative, we have to add a fraction here, dh over dt. There we have it. At this point, we're really just plugging in information. We know what dv dt is because it was given to us in the problem, 2 feet cubed per minute. We have an h to plug in because they told us we're looking for dh dt when h equals 1 foot. I didn't write it down here, but we probably should have actually written the given fact that dv dt is equal to 2 takes a little time here to work with this feet cubed per minute. Is that correct? Yes, per minute. So at this point, we know dv dt was given to us. They gave us an h to plug in. It was a changing dimension, so now we can plug it in after we do the derivative. And we have a dh dt is what we're looking for. So all we've got to do is plug these values in. So we know we've got feet cubed per minute. Feet cubed per minute is equal to 12, and again that's 12 feet, times the 1 foot that they told us to plug in, times fraction of dh over dt. And now we're just solving this. So 12 times 1 is 12, and we're going to divide that over to the other side. We should get a final answer here of 1/6. Right? 2 divided by 12. We've got a unit of feet cubed here. We've got feet times feet here is feet squared. Feet cubed divided by feet squared is going to give us just feet. per minute equals our fraction dH over dt. So, quick recap. Look at your shape, write the volume, or write the equation you need. In this case, we're dealing with a three-dimensional shape. We're dealing with a change in volume. Write a volume equation. Identify any constant values and plug them in. Look for an equivalence of some sort that will help you eliminate a variable. Once you identify which variable you're looking for dH dt, we need to keep h in the problem. So then we used our equivalent, plugged it in, and got our final volume equation here. We took our derivative of our volume equation, and now you can plug in your given information and solve for whatever rate of change is left over. Okay? I'll be back in a couple seconds with the second problem that I assigned for you yesterday.